section 4.5 today. And so we're going to be doing optimization problems. So your book gives some guidelines of how to solve these. We're going to be doing the same here. I give slightly different guidelines than them, but same concept. So the first thing you want to do is read through the problem and understand it, right? So that's the very first thing. So try to figure out what's being asked, what are you trying to look for, what's useful, what's not useful, and all this other one. Often it's very useful to draw a diagram. So draw a diagram, try to give something that makes sense to what you're trying to do, so that way you can visualize it. Then you're going to introduce notation, so assign a symbol of quality. So usually for optimization problems, you're going to try to maximize or minimize something. So we're looking here for absolute minimums or maximums for your equations, and so we're going to be using what we've learned earlier in this chapter. So you're going to introduce some notation, say this equals this equals that, that equals this. You're going to write out some equations based off of either the problem or what we know from outside that, and then we're going to solve for it, right? So let's just start diving in. All right, so in order to do this, so let's just start with the very first one. So here we have a farmer with a fence. And so a farmer has 200 feet of fencing and wants to fence a rectangular field along a straight river. And this is a super classic problem. So he needs no fence along the river. What are the dimensions of the field that he has the largest area? So here, we're going to have some sort of river here. And then he's going to build a rectangular field. And so we'll assume that this is straight enough that we'll just, this. Okay. And so in here we need to introduce some notation. So here we have 250 feet of fencing. So here's the important part. What do we want to do? We want to maximize the area here. So we want to maximize the area. That's what we're trying to optimize. What do we know? We have 200 feet of fencing, and we only need to do three of the 4 parts of our rectangle. So we've read the problem, try to understand it, and also do some notation. So let's just say whatever size we have x, this will also be x. So these is x. And if this is x, we'll leave that to be y. So, what do we know about the area? The area, so we'll use that. So here's some notation. This side is x, this side is y. Do I need to write it out? No, we're just... so the area is equal to x times y. So x times y. That's what we're trying to optimize this. We're trying to make this as big as possible. So area is what we're trying to make big as possible. So that's one thing we know. What else do we know? We have 240 feet of fencing, so we need at least one y distance, but the other y distance is not needed because it's the river, and then we'll have plus an x and an x, so plus 2x, and that's going to equal 2,400 feet. Okay. All right. So here we have this equals to be 2,400 feet. So what do we try to do? We try to get it all in terms of one variable. And so we're going to take these two equations. We want to optimize area. So let's try to eliminate one of the variables. And so what I'm going to try to get rid of right here is the y. Get rid of y. And so here I'm going to write this one as y equals 250,000 feet minus 2x. So we're going to move the x over, and then I'm going to plug it in here. So our area is equal to x times 240 minus 2x. I'll go ahead and leave off the feet for now. We know what it is. And so if we just crunch that through, we have area equal to 2,400x minus 2x squared. All right. So here we've established an equation we want to min or maximize. Well, how are we going to do that? Well, we're going to be using methods in section 4.1, 4.3. So we're going to look for critical points, right? And to do that, we're going to take the derivative. So a derivative is equal, with respect to x, will be 240 minus 4x. I'm going to set that to equal to 0 because we want to find a critical point where it's a local max and min, right? All right, so if we set that equal to 0, we solve for this, we're going to find x is equal to 600. Do we have other local maxes and mins? Yeah. We can have x, so x equals 600. Notice here I should put a little caveats. Let me put the caveats right here. Here we know x has to be greater than 0, right? X has to be greater than 0 because that means I would have negative bends. And that doesn't make any sense for our problem. We also want to say x is less than, x could be 0, and we also want x to be less than 120 feet because if we have 2 of them, that means I just have all x and no y, and that's also 0. And or I could have it all y and no x, which also is 0 for the area. So let's test all our points now. So what are we going to look here? Here's a critical point, and we also want to test our endpoints. And our endpoints in this case can be 0 and 1,100. So let's just test it real quick. So area at this point. So area, if I plug in 120 for my x, right? This is a function of x is equal to 240,000 times 1,200 minus 2 times 1,200 squared. That's all going to equal 0. If I type in area of the 0, so I'm testing my endpoints first, I'll get 240 times 0 minus 0. That also is 0. Alright, so let's test our other point real quick. We'll test 600. We'll test 600. And our 600 here, we're going to just plug in all our values of our critical point. So for 100, it's be 240 times 600 minus 2 times 600 squared. And that's going to equal to 72,000 feet. Okay. And so this is our answer. Or technically it should be feet squared, sorry. So the largest field we can achieve would be 720,000 feet square foot field using the dimensions of y of 600 on this side, and then if this is 600, then this y right here is so let's go ahead and write that down, where the sides of the field are 600 feet, and then if here y is equal to 600 feet minus 1,200 feet, so, and then the length, I'm going to say the length of our field is 120 feet. And so this is the best situation. Now, is there other situation? Sure. And it's not too terrible. Let me just show you just a little brief one. Let's just pretend I put 100 here and 100 here. And then what am I left over with? I'll have 220 up top, right? And it's not bad just to test another point just to see if you got everything correct. So this would be 100 times 220. So this is 200 and so this field is 200 and 220,000 feet. And notice how that is much smaller than our optimal right here. Okay. So that's kind of how you do this. So once again, you read through the problem, try to figure out what you want to optimize. In this case, it was the area of our field. Try to draw a picture, and then here we're going to write out in the notation, we're going to say x is our field, our side of the field, and y is the length, right? Then we write out equations, write out equations from define. So here we have our area is x times y. And then here we know that if we add up all our fencing, so y plus 2x, since we don't need to use this side, is 2,400 feet. Then once we write out the equation, we just try to make it into a single equation which we can optimize, and then we optimize that equation by finding the critical points and the endpoints. We test all those points, and we just pick whatever one's the max and min. Alright, so we're going to do this all again on the next page. Alright, I'm going to go ahead and zoom on in. Alright, so a cylinder can be, cylinder can is made to hold 1 liter of oil. find the dimension that will minimize the cost of the metal the manufacturer can. So what are we trying to? So what do we know here? We know we want to make a cylinder. So let's just go ahead and draw one real quick. Alright, so we have some sort of cylinder here. Or actually, I should probably do where that you can't see that. So we have some cylinder here. And we know that we want to hold one liter of oil. And we want to minimize the surface area, right? So minimize the cost of the metal. So let's go ahead and run through this real quick. So let's see which one do I show. Let's talk about the surface area. The surface area here. So let's just add an R, and then we'll have an H. So I'm introducing my notation. So I'm going to have R be my radius and my H be my height. Everything else can be determined from these two things. So I don't need to add any more notation. So the surface area, so the area of my can, is equal to the two little circles on the top and the bottom. So that's 2 pi r squared. So pi r squared is the area of the circle, and there's 2 of them because I have top and bottom, plus the area of my height, so it would be 2 pi r is the circumference of my circle, and then I'll have h times h will be the total surface area. So this is the area, and and what am I trying to do? I'm trying to minimize this one. So this one I want to minimize that. Alright, what else do I know? Well, I also know that I want the volume, and the volume here, so the volume here is equal to pi r squared, which is the surface area of that, times h, right? And I want this to equal to 1,000 centimeters squared, centimeters cubed. So 1 liter is 1,000 milliliters. So it's 1,000 milliliters, so I'm just going to do that way. That way I can write my dimensions at the end of the day in centimeters, because that will make the most sense for me, right? I guess it's just my programming. You could have written this as use different units, but this is just a unit I'm going to use because I know 1 liter is 1,000 milliliters, and a milliliter is 1 centimeter cubed. So that's what I'm using. Alright, so I want to minimize this. So what do I want to do first? Well, I have an h here and an h here, so I'm going to try to get rid of the h. So here, if I solve for h, I get h is equal to 1,000 divided by pi r squared. And I'm going to plug that into my a, so I get 2 pi r squared plus 2hr times 1,000 pi r squared. So this pi cancels, this r cancels. So I can really get 2,000 over r. And notice here I have to have my radius be greater than 0. And so here radius has to be greater than 0. It doesn't make sense to have negative radius. And so let's go from there. Alright, so let's go ahead and find its derivative. So now I have this. If I take this derivative, so this is area in terms of r. So I'm going to take with respect to r. So this is 4 pi r minus 2,000 over r would become, still be 2,000. Instead of plus, sorry, this plus becomes a minus because of the negative 1, r squared. We're going to set this equal to 0 and try to find our critical points. Alright. So here, our critical number, where does this equal to 0? Well, you solve for this, and you're going to get your critical number is going to be something kind of ugly. So it's going to be the cubic root of 500 over pi. And how you get that is just you multiply everything by r squared, clear out the r's, and then you just solve for r, just move everything over, so the 4 pi, so 4 would divide this, gives you the 500, the pi goes on the bottom, and then you take the cubic root of that, and so we go ahead and use this. So this is our critical number. So notice here, when r equals 0, we'd have to have some sort of infinite height, so that doesn't work. And if we have r be really, really large, our height gets really, really small, so that doesn't work. So this is probably our minimal value. So if we crunch through all of this, so if r equals this, what does our height equal, right? So, and just for ease, let's just say what this approximately equals. This approximately equals 5.42 centimeters. Okay, so approximately 5.42 centimeters. So that's what our radius is. We plug that into the h. But if we plug this into h, it actually ends up being not bad at all. So let me just do that real quick with you. So h, so what is our h? So our h is 1,000 divided by pi times the cubic root of 500 pi squared. And after a lot of simplification, this just equals 2 times r. So the height is just twice the radius. Which makes sense, and that should kind of match reality if you think about a soda can. A soda can, the radius is like kind of like almost twice the height. Not quite. It's a little bit. There's a little bit difference in that, but you're just trying to minimize things. And so we do this, and we get our answer. So here we have our answer. So this is that. But let me actually graph this with you. I want to graph this with you. I want to show you a graph of this and help you to visualize it. And sometimes using a graph is an amazingly good idea. So let's go ahead and get rid of that, and we'll just go. Let's go ahead and open up a Desmos. We're going to just graph this using Desmos. Here we go. All right, and we're just going to go ahead and put this in. So we're going to have 2 pi r squared plus 2,000 divided by r oops, let's just go ahead and instead of r, let's just use x, so Desmos is happier with life. There we go. Let's zoom on out. Oops, do I have everything in here? Here we go. So notice what we have here. So as we have our r come out, it's hard to see, so let me zoom on in a little bit. Okay. So here we can finally see the individual tick marks. So as r gets bigger, 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 and so notice right here at 5 centimeters in, because this is the origin, I just can't see it right now. It comes in, comes out, and then it just gets big and gets much bigger. So here we can just kind of look at that. So here, so the graph looks like, it's hard to see a little bit, but notice here, our graph matches what we calculated. Okay. And here we have a surface area, and here we get the answer for our surface area. Surface area is somewhere about a little over 550 cubic centimeters, so we end up doing quite well. All right, so that's how you do that one. So once again, what do we do here? We read the equation, we established some notation, figured out what we want to minimize. usually you'll have two equations, try to put one in term of the other, and then you get this equation, you find your critical point. This, for here, you test the endpoints, but the endpoints don't make any sense, and so this is the radius, this is the height, so the height would be roughly 10.84, right, centimeters, and that makes the, find the dimensions that will minimize the cost of the metal. Well, in this case, it's the radius equal to that, and the height equal to the here, and that gives you the least amount of metal. Okay, so those are the two dimensions. And we found that by finding the one critical point here. Notice this is only the positive version, since R must be positive. All right, let's just do one more of these, and then we'll call it good. All right, so find the point on the parabola that's closest to the point of 1, 4. So let's just kind of draw that in. And so let's go ahead and let's start with a picture. And this time, let's just use Desmos. I already have it up. Just reload it. Hi, reload. Yes. Leave page. There we go. Let's just do them. Here we are. We wanted the parabola of y squared is equal to 2x. Okay, so here we have this parabola. We want to find the point what is closest to 1, 4, which is right here. So we want to find which point is the closest. And so just by graphing this real quick, let's go ahead and just draw this in right here. We're gonna have a point right here. We understand that it should be somewhere within this range, right? We want to find something within here. If not, it doesn't make sense. So what equations do we have here? What equations do we have here? Well, we have the equation that's given to us. And so our variables are just x and y, right? We want to find which point on the parabola, what point exists here, that's the shortest distance from here. So we don't need an introduce notation, it's already all there. So let's write down what we want. Y squared equals to 2x, and what do we want to minimize? Distance. We want to minimize distance. Okay, and so distance is equal to the square root. In this case, it's going to be x minus 1 squared plus y minus 4 squared. So here, this is our point 1, and we're going to have some point here, xy, that must satisfy this equation. So since this is true, we know that x is equal to y squared over 2, and that way I can just plug that in for x. So we're going to get rid of that. So we have distance is equal to the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. And what are we trying to minimize? We want to minimize this distance d, so we want to minimize this. Okay. And in order to make our lives easier, let me just introduce a trick. If we minimize d, we're also minimizing d squared. Because if the distance is short, and distance has to be positive, squaring it is still, if we minimize d squared, that still becomes positive. But the reason we want to do that, and I'm going to say d squared is equal to some f of y. The reason I want to do that, it just makes my life easier. Because if I square this, I just have 1/2 y squared minus 1 squared plus y plus 4 squared. And then I don't have to deal with I do not need to deal with the square root. And so here we take this derivative. So if we take the derivative of this, you're going to get, well, the 2 comes out, so it'll be 2 1/2 y squared minus 1 y plus 2, because the 2 comes out, y plus 4, and nothing, right? And if I simplify this, this actually just simplifies to y cubed minus 8. All right, so y cubed mince 8, and so I want to set this equal to 0. So where's this equal to 0? Well, when y is equal to positive or negative 2, or it's like, hold on. When y is equal to 2, or imaginary units, right? And so here we have y equals to 2. So here's our 2. And does that match where we think it should be? Yeah, now if I test our endpoints, where are our endpoints? Our endpoints are like way out here in our parabola, right? And so we do not need to test these since we know that these will be much, much, much larger. So this, we can just use our critical point here. So we just said y equals 2. Well, if y equals 2, what does x equal? Well, 2 squared plus that, so that means x is 2 squared divided by 2, which is also 2. Okay? So we have 2 squared divided by 2, which is also 2, so we have the point 2, 2 is the closest. Okay? And so here, we've determined what the closest point. Does that match our observation? Sure, let's look kind of here, right? Let's look here. If I'm here, and I think I go to 2, 2, that's just, that's kind of a basic straight line, straightforward, right? And so here, that's the closest distance. Because if I was here, it'd take a little bit longer to get, and so I will be, so here's our closest point. And so everything we go from here would be a little bit larger, and here you can see how it's much larger. And as we go this way, of course, our distance gets much larger. So once again, so how you solve each of these problems is you draw a picture, introduce notation, you read through it, try to figure out what you're trying to minimize. I want to minimize distance, so I need this. I drew a picture. I knew I want to hit somewhere around here, which I did, right? I write out my equation, so one of these equations was given to us, the other one's the distance formula, which is what we wanted to minimize. And this one we used a little trick. Here I'm going to say, if I'm minimizing distance, it's the same thing as minimizing distance squared. You can use this a lot of the time. Just say if I'm minimizing a number, I'm minimizing the square of that number, will still be minimizing that number as long as that number has to be positive, right? And distance has to be positive. After that, so we just rewrite this as a different function. That way the derivative became a lot easier to do. And after I took a derivative, set it equal to 0, find the critical point. That is my minimum in this case. You could use other methods, which we've learned else, to prove that that's a minimum, but in this case we just know, so we don't have to do the proof. And so here we have 2, and then we plug that in and get the other one. So y gave us this 2, and then we plug it in, figure out what x was, and that's 2, so 2, 2 is the shortest point. Okay, and that's the end of this video.